Just near, walls and text crystal clear. Got you telling me Wilson Tech Talks, yeah, we'll wire. Sparking minds and lighting fires. Click subscribe, don't miss the flow. Tech Today, where it'll go. Bits and bytes, they dance all day. Circuits buzzing a bright ballet. Code and dreams pave the way. Wilson Tech Talks, yeah, we're wired. Sparking minds and lighting fires. Click subscribe, don't miss the flow. Tech Today, where it'll go. Bits and bytes, they dance all day. Circuits buzz in a bright ballet. Code and dreams pave the way. Wilson Tech Talks, yeah, we're wired. Sparking minds and lighting fires. Click subscribe, don't miss the flow. Tech Today, where it'll go. From screens to dreams, the journey's on. Wilson Tech, we're breaking dawn. Talk the talk, let's tech it strong.
Welcome, fellow explorers, to the Deep Dive. Today, we're plunging into a world that, for many of us, is pure escapism. Video games.
Yeah.
But beneath the dazzling graphics and immersive storylines, especially in those huge, sprawling online worlds like MMOs, there's an incredible complexity.
There really is.
We often enjoy these digital realms without ever realizing the intricate software architecture that's tirelessly working behind the scenes, keeping everything running smoothly.
It's kind of amazing when you stop and think about it, isn't it? How we can seamlessly interact in a shared, persistent universe with thousands, maybe millions of other players. And we just take it for granted. We don't think about the engineering marvel that makes it all possible. Every character movement, every item picked up, every single interaction, it all hinges on really robust, well thought out design.
It truly does. So our mission today is to give you a shortcut, maybe a fast track, to understanding the core building blocks and best practices of game architecture.
Right. Sort of peel back the curtain.
Exactly. We're going to unpack the fundamental philosophies that underpin these big software projects, explore the specific components that make games tick, and then really dive deep into the unique challenges and, frankly, the ingenious solutions tailored for MMOs.
Yeah, the MMO part is fascinating.
We'll even draw some lessons from pioneers like Ultima Online, which is just incredible history. And we'll reveal the powerful principles like the solid principles that guide developers in creating robust, maintainable code, often using languages like C#, which is pretty common in the field now.
Definitely. Get ready for some hopefully surprising insights and some practical wisdom from the minds behind these really complex systems.
And to set the stage, our insights today are drawn from, quite a diverse stack of sources.
Yeah, we've pulled from a really insightful YouTube talk on architecting large software projects, some excerpts from a foundational book on game programming patterns.
Oh, good stuff there.
Yeah, really solid. Plus a cutting-edge research paper on big data management specifically for MMOs, which is a whole other beast. And even snippets from lively discussions on online developer forums alongside, historical accounts of game genres and programming paradigms. It's quite a mix.
It's a rich tapestry of knowledge, for sure. So with that understanding of what this deep dive entails, let's zoom in on the foundation. What is game architecture and why does it matter?
Okay.
Because let's be honest, when you think game development, you might picture artists creating stunning visuals or designers crafting compelling narratives.
That's usually the first thing, yeah. The shiny stuff.
But good software architecture for games isn't just about the fancy graphics or the complex AI.
Right.
It's fundamentally about organizing the code that lives between all these elements.
Right. It's the plumbing, the wiring in the walls.
Exactly. It's the invisible scaffolding that holds the whole structure together, making it either, a joy or a grinding chore for the developers who work on it every day.
That's precisely it. And we all have an intuitive sense of good versus bad code bases, don't we? You've probably suffered through a code base so messy it felt like wading through treacle, right? Where every change feels like you might break 10 other things.
Definitely had that experience.
Right.
It's awful.
Or if you're lucky, you've worked with beautifully designed code, which feels like, I don't know, a perfectly appointed luxury hotel where everything just works, everything's in its place.
That's a great analogy.
The difference is purely in that organization. It dictates the experience, not just for players, but crucially for the developers themselves. It impacts their productivity, their ability to fix bugs, even their sanity, frankly.
Yeah, absolutely. And one of the most striking points the sources make, and I think this is crucial for you listening, is that the ultimate test of truly great design isn't how pretty your code looks on day one. It's resilience to change. If code never changes, maybe because it's perfect, which is rare, or because it's so wretched no one dares touch it.
Which is probably more common.
Probably. Then its design is pretty much irrelevant. The moment you want to add a new feature, fix a bug, or refactor something, that's when good architecture proves its worth.
Yeah.
How easily can you pivot? How quickly can you adapt? That's the real metric.
Indeed. And even before you can make a change, you have to understand what the existing code does. This is often the most time-consuming part of programming. It's this slow, almost like a primate brain process of understanding, loading all the relevant pieces into your mind.
Yeah, that knowledge and cranium idea they mentioned.
Exactly. This is where decoupling code becomes such a key strategy. When two pieces of code are tightly coupled, you can't understand one without understanding the other. You have to load both into your head.
Right.
Decoupling allows you to reason about each side independently. So the core goal of software architecture, really, is to minimize that knowledge and cranium you need before you can make progress.
Makes sense.
This also dramatically reduces how much a change in one area ripples throughout the rest of the game, preventing those cascading failures we just talked about, where fixing one bug creates 3 more.
Okay, so if it's so fundamental to success, what's the catch? Because it sounds like everyone should just do this perfectly all the time.
Well, good architecture doesn't come free. That's the thing. It takes real effort, discipline, and constant maintenance. You have to treat your code base like a garden.
I like that metaphor.
Yeah, you're continually weeding and pruning to keep it healthy. It's not enough to just put in new plants. You have to care for the existing ones, refactor old stuff, pay down technical debt.
Which is so different from the temptation of just one tiny little hack to solve an immediate problem.
Oh, exactly. That quick fix feels good in the moment, but it can quickly unravel a beautifully designed system and leave behind this growing pile of technical debt that slows everything down later.
And that leads to a crucial tension, right? What the sources call the triple threat of speed in game development.
Yeah, this is a really important balance. You're constantly juggling 3 kinds of speed. First, there's long-term development velocity that's about maintainability, how quickly your team can add features over the project's entire lifetime.
Right, keeping that pace up.
Then there's game execution speed, pure performance, how fast and smoothly the game runs for the player, frames per second, loading times, all that.
Critical for player experience.
Absolutely. And finally, there's short-term feature delivery speed. This is about rapid prototyping, getting new ideas on screen quickly, testing things out.
And these 3 are often fighting each other.
They're often in opposition, yes. You have to make careful trade-offs. For instance, an architecture optimized for ultra-high performance might be really rigid and slow to extend. Adding a new feature might require major surgery.
Okay.
Whereas one built for rapid prototyping might perform poorly when you actually scale it up, or it might become a maintenance nightmare down the line. Finding that balance is key.
Okay, so having covered what good architecture is and why it matters, let's maybe zoom out a bit. What are the overarching philosophies, the bedrock principles that guide not just game developers, but anyone building truly robust, large-scale software?
Right. These are kind of the high-level goals. First up, optimizing for dependability. The ultimate aim here is software that ideally lasts forever and never breaks.
A lofty goal.
It is. But the idea is to write explicit code that is truly finished when it's written. You want to avoid those trivial fixes later on, because even small fixes cause constant context switching. You have to stop what you're doing, load unfamiliar code into your head, fix someone else's minor bug.
And those little interruptions just kill productivity, don't they?
They add up massively as projects grow, leading to significant slowdowns. The source mentioned this preference some C programmers have for sticking to old standards like C89.
Why C89 specifically?
Because it's highly dependable, it compiles absolutely everywhere, it essentially lasts forever. The standard is stable. But the critical takeaway isn't about C89 itself. It's that these rules of dependable coding are language agnostic.
Right, so C++, EA, Python, C#, Predator, the principles apply.
Exactly. The point is to make your code robust and predictable, because it's almost always faster in the long run to write 5 lines of explicit, well-tested code today than to write one clever line and then have to go back and edit it 5 years from now because it broke due to some implicit assumption you made.
That Python 2 to 3 transition is a good example of that risk, right?
Mm-hmm.
Breaking changes in the language itself.
A prime example of a language implementation risk you want to mitigate for long-lived software. Dependability is key.
Okay, so beyond dependability, what else?
Ensuring extendability. This is all about designing systems so you can easily add new features and capabilities in the future without needing to fundamentally rewrite large parts of the code. It's building for tomorrow's unknown needs, anticipating growth without, over-engineering for specifics you might never need.
Building in flexibility.
Precisely. And closely related to that is achieving team scalability. For large projects, the goal is to break them down into many smaller, insulated projects or modules.
The one person per module idea.
Ideally, yeah. If each section is manageable by one person, it minimizes the need for huge team meetings and all that coordination overhead. This directly contributes to overall development velocity. If each module is a distinct black box that one person is responsible for, it streamlines the whole process, avoids the too many cooks problem.
Which naturally leads to maintaining development velocity.
Exactly. This principle is all about counteracting that common problem, where software projects just get slower and slower over time as the code base grows and gets more complex. The aim is to maintain a consistent, predictable pace of getting things done. You want a system that doesn't resist change but actually invites it, makes it easy.
Then there's reducing risk. This seems crucial.
Absolutely. Things will go wrong in complex projects. It's inevitable. So you need to proactively identify and insulate your system from likely failure points.
Like what kind of failure points?
Well, external factors like changing platforms, maybe an OS updates its API unexpectedly, or terms of service change, or even just user popularity shifts dramatically, forcing you to scale up or down really fast.
Right. Things outside your direct control.
And internal things, too. Language implementations, like we discussed, evolving hardware requirements, shifting project priorities from management, or even the loss of key developers, those star programmers who hold critical, often undocumented knowledge in their heads.
The bus factor.
Exactly. Insulating against these helps avoid a lot of little failures, adding up to a big chance of system-wide failure, which can absolutely kill a project.
And finally, the cornerstone supporting a lot of this.
Yeah.
Mastering modularization.
Yes. The philosophy of black boxes. Modules whose internal workings are hidden away, exposed only through clear, well-documented APIs or protocols.
So you can use it without needing to know how it works inside.
Precisely. You trust it to be rock solid and just work. Think about plugging a USB drive into a computer. You don't need to know the intricate details of its firmware or the USB protocol itself to use it.
That C header file example was good too. Clearly defining the public interface while hiding the internal complexity.
Exactly. It defines what the outside world can see and use, hiding everything else. This design directly supports that one person per module ideal we talked about. Each small, self-contained unit can be managed by a single developer, drastically reducing their cognitive load and the communication overhead for the whole team.
Okay, that gives us a solid philosophical grounding. Now let's zoom in on the specific components. What are the actual building blocks and layers of game architecture?
Right, let's get into the nuts and bolts. A standard game, at its core, relies on several internal elements working together. You've got the graphics
The
engine.
visual powerhouse?
Yeah, responsible for drawing everything on screen, managing resolution, VSync, making sure scenes transition smoothly. It handles all the visual output.
And the audio side.
The sound or audio engine. This contains all the algorithms for sound effects, music playback, spatial audio maybe. It uses dedicated audio APIs like OpenL or SDL audio or platform-specific ones to bring the game world to life audibly. Everything from footsteps to explosions to dynamic music cues.
Okay. And rendering.
That falls under the rendering and vision input engine. This is what actually produces those dynamic 3D animated graphics. It uses techniques like rasterization or maybe ray tracing these days.
Built on top of APIs like DirectX or OpenGL.
Often, yes, or Vulkan or Metal.
Yeah.
These APIs give the engine access to the graphics hardware. This engine translates the game world state into the pixels you see on screen, and it also typically handles the camera view based on input.
Speaking of input.
Crucial role for I/O devices, your mouse, keyboard, joystick, gamepad, monitor, even touch screens now. These are absolutely fundamental for interactive gameplay. They're the bridge between the player's physical actions and the digital world.
And behind the scenes, supporting these.
You have things like DLL files, dynamic link libraries. These contain reusable code and instructions that different programs can call upon. It avoids duplicating the same code in multiple places.
Like shared libraries.
Exactly. And then you have the drivers and device APIs themselves, like DirectX or OpenGL that we mentioned.
And these are vital because they abstract the hardware, right?
Absolutely vital. They provide hardware-independent access to various system devices. This means games can function across lots of different PC setups, for example, without the game developer needing to write specific code for every single graphics card or sound card out there.
So DirectX handles that on Windows.
Right. It's a suite of APIs from Microsoft for graphics, sound, input, networking. OpenGL is its main cross-platform counterpart, used widely on Linux, Mac, mobile platforms, though Vulkan is gaining ground there too.
Got it. So those components work together to make the game run.
They form the kind of internal and external architecture that enables that seamless player experience on different machines.
Now, moving up a level, you mentioned layered architecture for portability and reusability. Let's talk about the platform layer.
Yes, this is a really important concept. It involves abstracting away all the platform-specific details. Think about how a window is created and managed on Windows versus macOS versus Android. They're all different.
Or handling input from a mouse versus a controller versus touch.
Exactly. Or dealing with varying screen resolutions, different aspect ratios, identifying safe areas on a phone screen so your UI isn't hidden by a notch or rounded corners.
So the platform layer hides all that messy stuff.
It aims to create a single, unified interface for all these wildly different hardware and operating system quirks, so the rest of your game code doesn't have to care.
The example from the sources was that Betray header.
Right. Yeah, that was a great illustration. It served as this unifying bridge for fundamental platform interactions, creating windows, processing user input. Initially, it wrapped a library called SDL 1.0.
But the key was it could be swapped out.
The genius was its design. You could effortlessly swap out the underlying backend to support other platforms like native Win32 calls or Android's NDK, ensuring the game's higher-level code remained blissfully unaware of the platform's specifics. It just talked to Betray.
And that minimal demo application was important for testing.
Crucial. You develop this simple test bed while building the platform layer. It just opens a window, reads mouse input, draws a triangle maybe. It's essential for porting and testing that foundational code. It lets you consolidate those disparate platform functionalities like making all button presses, whether from a controller, keyboard, or mouse, trigger the same kind of event in your game logic, or treating all touch inputs like mouse pointer events.
Okay, platform layer handled. What's next?
Then there's often a drawing layer. You need a basic drawing API on top of the lower-level rendering engine or platform graphics. Something that can handle drawing lines, rectangles, surfaces, loading images, rendering geometry, maybe applying shaders.
And this should also work across different backends, like OpenGL or Vulkan.
Ideally, yes. Similar to a library the source mentioned called Relinquish, which provides a consistent drawing interface regardless of the complex rendering technology underneath, like OpenGL or Vulkan. This abstraction means your game logic doesn't care how it's drawing. It just calls a generic drawSprite or drawLine function.
Makes sense. And the text layer. You said that was a good example of forward-thinking API design.
Yes. This really illustrates the principle. You might start with the simplest possible implementation, say a basic bitmap font where each character is just a little image, quick and easy to get started.
But the API itself should be more ambitious.
Exactly. You design the interface to anticipate future needs, even if you don't implement them immediately. Things like UTF-8 support for multiple languages, text coloring, kerning for precise letter spacing, maybe support for TrueType fonts for crisp, scalable text.
So other developers using this layer can code as if those features exist.
Precisely. They can start building UIs using colored text or assuming proper language support right away using the well-designed API. Later, when the nicer, more complex text rendering implementation arrives, maybe using FreeType library or something, their code just works without any changes.
Because they were coding against the stable API, not the initial simple implementation.
Right. This avoids that trap of creating a good enough for now API that you later deeply regret because it's impossible to extend without breaking everything that uses it. You build the interface once, make it forward-thinking, and then you can upgrade the implementation behind the scenes whenever needed. That's core to good architecture.
Okay, that's clever. What about the UI toolkit itself? Buttons, sliders, checkboxes.
Well, the source made an interesting point here. Building your own UI toolkit for these elements, while it might seem like reinventing the wheel up front,
Seems like a lot of work.
it can actually be easier and far more portable in the long run than trying to wrestle with platform-specific native UI implementations across multiple operating systems, especially if you need your game or application to look and feel exactly the same everywhere.
Ah, so you get perfect consistency.
Yes.
Uh,
When you build your own toolkit, you control its behavior and appearance perfectly across all your target platforms. Text input is usually the trickiest part, often requiring some deep integration with native OS features for things like virtual keyboards or complex input methods. But for most other UI elements, buttons, sliders, windows rolling your own provides immense control and ensures that consistency.
okay. And then the sources mentioned helper libraries as a kind of superpower.
Yeah, that's a good way to put it. This is about the strategic value of building and owning your own comprehensive suite of reusable helper libraries. These are components for common functionalities you'll need again and again.
Like what?
Things like robust file parsing for different formats, maybe a simple physics engine if you need one, interfaces for scripting languages like Lua or Python, efficient data storage solutions, and resilient networking code.
The example was Testify for networking.
Right. A library like that acts as a sophisticated translator. It abstracts away all the intricate low-level details of how network sockets work, connection management, error handling, different protocols maybe. So your game developers can just focus purely on sending and receiving game-specific messages like player moved or use item. They don't get bogged down in the network plumbing.
And having these libraries is strategic because
Because this shared foundation is incredibly valuable, it allows for rapid development of any future product you build. It also insulates your applications from changes in underlying third-party APIs or platform specifics. Once you've built these well, you rarely have to worry about those low-level details again. And you can improve them under the hood, make them faster, more robust, without breaking the applications that rely on them. It's a huge long-term investment.
that makes a lot of sense. Okay, let's get to the heart of it. The application core and plugin architecture. The idea of generalization here sounds powerful.
It really is. Finding a fundamental primitive to structure your entire application around can dramatically simplify things. The source gave some great examples. Unix's philosophy, where everything is a file.
Right, allowing powerful piping of data between commands.
Or visual effects software like Houdini and Notch, where everything is a node graph. Houdini is famous for this procedural approach. Every operation, from creating a sphere to adding noise to transforming it, is a node in a graph. Artists build incredibly complex effects by just connecting these simple building blocks together.
So it provides one consistent way of thinking about everything.
Exactly. This everything is X approach simplifies complexity by giving you one powerful, consistent mental model for the entire application.
And the contrast was with something like Unreal Engine.
Yeah, the source pointed out that Unreal uses a mix of things. C++ code, blueprints, its visual scripting language, and scene graphs. It's incredibly powerful and versatile, no question. But sometimes that mix can make it harder to generalize everything as easily, and it can lead to integration challenges between the different systems if you're not careful.
So it highlights that distinction between the basic data format, the primitive,
Like bitmaps in Photoshop or Nuke, compositing software.
and the structural way that data is organized and processed.
Like layers in Photoshop versus node graphs in Nuke or Houdini. Recognizing these two distinct aspects, the data itself and how you structure operations on it is really crucial for making informed design choices early on.
Once you've identified that primitive, how do you design the core? The source mentioned treating it as a black box.
Right. The application's central data storage, the core, should be designed as a black box. For a video editor, this might be the timeline data structure. For a jet fighter's flight control system, it's the complete state-of-the-world position, velocity, fuel, weapon status, everything.
And this core manages the data and enforces rules.
Yes. It manages the fundamental data, it enforces guarantees or invariants like ensuring video clips don't have negative time duration or that an aircraft's thrust value is never negative, and it can even handle complex features like under-rato functionality internally, abstracting these tricky complexities away from other parts of the system. It becomes the single reliable source of truth for your application's fundamental state.
But you don't want this core to become huge and monolithic.
Exactly. That's where the plugin architecture comes in. To prevent the core from becoming this unwieldy beast that nobody fully understands, you implement a plugin system. The core defines clear APIs for specific functionalities.
Like loading different video formats.
Perfect example. The core says, I need something that can load MP4 files, and it defines an interface for that. Then an external plugin provides the actual implementation, using maybe Fmpeg library or something. This keeps the core itself small, focused, and ideally manageable by one person or a very small team.
While allowing potentially huge extendability through plugins.
Exactly. The source mentioned an application called Stellar 2.0 for theatrical lighting control. It uses plugins for all its visual effects. The core is tiny, just manages nodes and parameters, but complex effects like shimmering spheres or color ramps are all external plugins. This allows easy expansion without ever touching or destabilizing the core code.
And a really powerful outcome of this is decoupling the UI.
Yes. The ability to completely separate the user interface from the core logic. The UI, which might even have its own plugins for different panels or custom widgets, just talks to the core via its well-defined API.
So you can completely rebuild the UI without touching the core.
Absolutely, or modify it extensively. Even more powerfully, the core could be used completely headless as a command line tool for automated rendering, perhaps, or running on a server without any graphical interface at all. This demonstrates huge flexibility and reusability.
That washing machine API analogy was good too.
Yeah, the API just describes the parameters and functions: wash temperature, spin cycle, speed, start, stop. It doesn't need to know it's a washing machine. Any smart home interface can connect to it because the API clearly states what it can do and what data it needs. It's highly generalizable.
Okay, this architectural foundation is clear. Now, let's shift focus to where things get really massive. Massively. Multiplayer online, MMO, game architecture.
Right. This is where the scale introduces entirely new dimensions of complexity. The principles we've discussed are still fundamental, but what happens when your game world needs to handle thousands, maybe millions, of players interacting simultaneously in real time?
That's the challenge, isn't it? Let's trace their history a bit. It started with text-based games.
It did. The lineage goes back to the late 1970s with early text-based multi-user dungeons, or MUDs. These were inspired by single-player adventures like Zork, but allowed multiple people to connect via early computer networks and interact in the same world. Very pioneering stuff.
But getting them commercial was tough initially.
Very tough. Early attempts faced huge hurdles, mainly cost and limited network access. Games like the 1991 Neverwinter Nights, which actually had primitive graphics.
On AOL, I think.
Yeah, or services like CompuServe. And 1992's Legends of Future Past, which introduced MMO-like quests and live service elements via paid administrators acting as game masters. These were incredibly expensive, like up to $12 per hour back then.
Wow. That's prohibitive.
Totally. It severely limited their mainstream appeal. You had to be pretty dedicated or wealthy to play regularly.
So what changed? What was the catalyst for the MMO boom?
The big shift was the relaxation of NSFNet policies in the U.S., which basically allowed commercial traffic on the internet backbone for the first time. That opened the floodgates.
And then came Ultima Online.
And then in 1997, the true MMORPG, as we generally think of it, was born. Ultima Online. Its creator, Richard Garriott, famously coined the term MMORPG. UO was revolutionary. It offered players unprecedented freedom.
Yeah.
You could roleplay, interact, fight, craft, build houses, run shops. It created these incredibly vibrant online communities within its fantasy world of Britannia. It was a massive departure from the linear single-player RPGs common at the time.
And technically, it was a marvel for its time.
Absolutely remarkable. It managed to achieve astonishing scale, supporting thousands of concurrent players per server and millions of persistent objects in the world. Think about every item dropped, every player-built house, every vendor shop, it all persisted.
And this was on hardware from 1995.
Yes, which was incredibly modest. by today's standards. They pulled this off through completely custom solutions. They couldn't use off-the-shelf databases. The performance just wasn't there, so they built their own object persistent systems, their own server architecture.
And the networking.
Their networking protocol was designed specifically for dial-up modems, which were common then. It was described as extremely reserved, meaning it was very non-chatty, sending only the absolute minimum data necessary. This resulted in surprisingly low daily traffic, maybe just a few megabytes per player per day, which was crucial for accessibility on slow connections.
That's incredible efficiency. And they invented sharding.
They did. The Ultima Online dev team actually coined the term shard to explain to players how the game world was split across multiple physical servers to handle the huge player load. Each server was a shard of the world. That concept became so influential it spread throughout the database industry later, becoming a standard technique for scaling massive datasets.
Wow. So UO really set the stage. What came next?
After UO, the genre truly exploded. You had the big three of early graphical MMOs, Ultima Online, EverQuest, which launched in 1999 and became hugely popular, and Asheron's Call, also 1999.
Was there worry about too many games too soon?
Believe it or not, yes. There was actually a fear of oversaturation very early on. Electronic Arts, UO's publisher, even canceled a UO sequel called Ultima Worlds Online. Origin in 2001, partly because they thought the market was already too crowded.
If only they knew.
Right. But the genre just kept growing. You had other influential titles emerge, like Ragnarok Online, which absolutely dominated the Asian market with something like 25 million registered users at its peak, building its own massive community.
And then the 800-pound gorilla arrived.
And then came World of Warcraft in late 2004. Why? It didn't necessarily invent many new features, but it took all the best ideas from its predecessors, questing from EverQuest, the accessibility, maybe some of the art style influences, and polished them to an incredible degree, making it super accessible and appealing to a much broader audience.
And it just exploded.
It hooked millions, led to a huge wave of clones trying to capture that magic, and defined the genre for a decade. Now we have the sort of ever-shifting big five or so of popular MMOs, WoW is still there, but also Final Fantasy XIV, Elder Scrolls Online, Guild Wars 2, maybe others depending on who you ask. The landscape keeps evolving.
Okay, so these games are massive. Let's tackle the big data challenge. Modern MMOs generate just insane amounts of data, right?
Phenomenal volumes. We're talking potentially terabytes daily from millions of concurrent players, logging actions, chat, inventory changes, positions, everything.
And traditional databases just can't keep up.
That sheer scale quickly overwhelms traditional relational database management systems, or DBMS, like your standard SQL databases. They become a huge performance and scalability bottleneck. You simply can't handle that kind of write load and query complexity efficiently with conventional relational tech. It leads to lags, slowdowns, even server crashes if the database can't cope.
So what's the solution? Big data technology.
Exactly. The approach discussed in the research paper is to leverage big data tools. Specifically, using NoSQL databases is key. The paper focused on Cassandra as a strong candidate.
Why Cassandra?
Well, it's open source, it's non-relational, it's column-oriented, and crucially, it's decentralized. It uses a peer-to-peer structure, so there's no single master server that can become a bottleneck or a single point of failure.
Which is great for availability.
Absolutely. This allows it to store massive amounts of unstructured or semi-structured data like player logs, chat history, endless inventory updates, dynamic game state changes, and it scales horizontally. You just add more nodes to handle more load.
How does it handle writes so well?
It uses log-structured updates, which are very fast for writing new data. It caches frequently accessed data in memory for quick reads, and periodically compacts data on disk in the background to maintain efficiency. It's really optimized for high write throughput, which is exactly what you need for constantly changing game states.
And what about analyzing all that data? For business intelligence or game balancing?
That's where Hadoop often comes in. The paper suggested integrating Hadoop with the Cassandra nodes. While Cassandra excels at fast writes and reads of specific rows, like a player's current state, Hadoop is much better suited for complex, high-performance data analysis across large data sets.
So running queries like, what's the average time players spend in this zone? Or which items are being traded the most?
Exactly. Tracking player behavior, identifying potential exploits in the economy, balancing drop rates, those kinds of analytical tasks. Hadoop is built for that kind of large-scale batch processing.
But you don't throw out relational databases entirely.
No, the practical approach is often a hybrid database strategy. You'd still use traditional RDBMS like MySQL or PostgreSQL for parts of the system that are less data intensive or where relational structures and strong consistency are actually beneficial.
Like player counts.
Player account data, subscription information, maybe website backend stuff, things that don't change constantly and benefit from the guarantees of ACID transactions found in relational databases. You use the right tool for the job.
Okay, let's dive a bit deeper into Cassandra's specifics for MMOs. Performance.
As mentioned, its decentralized nature is key for robust write performance. Writing game state updates doesn't bottleneck through a single master server. It spreads the load, avoiding network congestion and single points of failure.
What about data consistency? NoSQL often trades consistency for availability.
Cassandra offers tonable consistency. You can configure per operation how many replicas must acknowledge a write or agree on a read. This is often managed via something called read repair, where inconsistencies can be detected and fixed during reads. There's a trade-off. Requiring more replicas to agree improves consistency but can slow down reads. However, it uses timestamps for versioning, so it can usually resolve conflicts based on which update happened last.
How is the data actually organized or partitioned?
Typically, game data, like a character's state or an object's properties, would be managed within a single row in Cassandra, identified by a unique key, like character ID. The data is then horizontally partitioned across the cluster based on these row keys. This allows for very high-performance access to a specific character's or object's state because the system knows exactly which node hold that data.
And the schema design is different from SQL.
Very different. Instead of rigid tables with predefined columns and relationships enforced by foreign keys, Cassandra uses dynamic column families. The design is driven by your query patterns, not just your data structure. Meaning you often increase data redundancy, you denormalize. You store all the data that you anticipate needing to query together within the same column family, even if it means duplicating some information.
I do that.
To avoid expensive join operations at read time, joins are notoriously difficult to scale in distributed systems and can become huge performance bottlenecks. By pre-joining the data, essentially, into wide rows based on expected queries, you make read operations much, much faster. It's a fundamental shift from relational normalization.
So did the research show this actually works for MMOs?
Yes, the evaluation results were positive. They found that Cassandra could meet the demanding performance requirements of MMUs. It showed linear scalability, add more game servers, add more Cassandra nodes, and performance scales predictably. Read performance generally improved with more nodes, more replicas potentially available, while write performance remained remarkably stable even under heavy load thanks to its architecture.
And Hadoop helped with analysis.
Yes, integrating Hadoop performed better for analysis tasks, especially read-heavy analytical queries across large datasets compared to trying to do those complex queries directly in Cassandra alone. It solidified the idea that this kind of big data architecture is a viable and powerful approach for modern MMOs dealing with massive scale.
Okay, data handled. Now, the real-time interaction. Multiplayer server design patterns. Let's start with communication. Client-server protocols, TCP versus UDP.
Right, the classic choice. TCP, Transmission Control Protocol, is reliable, ordered, and full duplex. It guarantees that packets arrive and arrive in the correct order because it handles acknowledgements and retransmissions.
So that sounds good for games, right?
Yeah.
You don't want commands getting lost.
It's ideal for certain types of games, yes. Turn-based games, strategy games, or any situation where every single command must get through and in the right sequence. The trade-off is higher latency because of that overhead of ensuring reliability.
And UDP.
UDP, User Datagram Protocol, is the opposite. It's faster, lower latency, but unreliable. It just sends packets out without any guarantee they'll arrive or arrive in order.
Why would you ever use that?
For high-speed, real-time games like first-person shooters or racing games. In those scenarios, getting the latest update quickly is often more important than getting every update reliably. If a single packet showing a player's position is lost, it's usually okay because the next packet a few milliseconds later will correct it. Sacrificing a little reliability for lower latency is often worth it for that real-time feel.
The example RPG in the source used TCP.
Yes, it specifically chose TCP. Because it was described as turn-based or having less stringent real-time requirements and prioritizing global accessibility, meaning players might have less reliable connections, the guaranteed delivery and order of TCP were more important than shaving off milliseconds of latency.
Okay. And beyond TCP/UDP, you need an application layer protocol.
Absolutely. TCP and UDP just handle sending bytes back and forth. You need to define the meaning of those bytes. For large distributed systems like games, you typically design a custom, flexible, and powerful application layer protocol.
What might that look like?
It could involve sending messages formatted in XML, or more likely JSON these days, or even a custom binary format for efficiency. These messages would have specific codes or types like player move, chat message, usability, and associated parameters like coordinates, message text, ability ID. It's the specific language your game client and server speak to each other.
Got it. Now, how the server actually handles all those incoming connections.
Yeah.
The network module I/O strategy. Blocking versus non-blocking.
Right. This is about how the server manages input-output operations on the network sockets. The older, simpler approach is blocking I/O. In this model, the server typically creates a dedicated thread for each connected client.
That sounds resource intensive.
It can be. Very.
It,
If you have thousands of players connected, you have thousands of threads. Each thread consumes memory, and many of them might just be sitting idle, blocked, waiting for data from the client. This limits the number of concurrent connections you can realistically handle on a single server, due to memory constraints and context switching overhead between threads.
like having a separate receptionist for every single person who walks into the building, even if they're just waiting.
Exactly that analogy. It doesn't scale well.
So the alternative is non-blocking I/O, NIO.
Yes. NIO uses a different model. Instead of one thread per client, it uses a small predefined pool of threads. These threads use mechanisms like selectors in Java NIO or event loops to monitor many connections simultaneously. A single thread can check hundreds or thousands of connections to see if any have data ready to read or are ready to receive data.
So a few very efficient receptionists handling everyone.
Perfect analogy. It handles thousands of concurrent connections much more efficiently, with a significantly smaller memory footprint. There might be a tiny, tiny delay in milliseconds as the thread cycles through checking connections, but the scalability benefits are huge.
And this is generally preferred for online games now.
For many, yes, especially those needing to support a large number of concurrent players, like MMOs or even many mobile games. Even if it's turn-based, like the RPG example, where ultra-low latency isn't the absolute top priority, the memory efficiency of NIO is a massive advantage when you have potentially tens of thousands of players connected to a server cluster.
Frameworks help with this.
Definitely. Frameworks like Netty in the Java world or using asynchronous programming patterns like async-await with sockets in C# make implementing non-blocking I/O much easier than trying to do it manually with low-level system calls.
Okay, handling connections efficiently is one thing.
Right.
What about concurrency management? Multiple players interacting with the same stuff at the same time.
This is a critical and often very tricky challenge in any multiplayer environment. You have many players potentially executing code concurrently on the server, all trying to access and modify shared resources.
Like what kind of resources?
Game locations is the spot occupied. Items, can two players loot the same chest? Character states, what happens if two players attack the same monster simultaneously? Shared inventory, like guild banks.
And the problems are?
Resource safety preventing data corruption if multiple threads modify the same data structure without coordination. Access fairness, ensuring players get fair access to resources, preventing starvation where one player is constantly blocked, and critically, preventing deadlocks.
Deadlocks, where everything just freezes.
Exactly. Where two or more threads are stuck waiting for each other to release a resource that the other one holds, thread A waits for resource X held by thread B, and thread B waits for resource Y held by thread A. Neither can proceed. It can bring the entire game server, or at least part of it, to a grinding halt.
How do you manage this? Locks.
Solutions often involve careful use of locking mechanisms, like mutexes or semaphores, but locks themselves can cause deadlocks if not used properly. Other approaches include using atomic operations provided by the hardware language for simple updates, designing lock-free data structures, which is complex, or using message queues or actor models to serialize access to shared resources. It requires very careful design.
And you also need to save everything. Persistence and performance.
Yes, for persistent game worlds, efficiently saving and loading the game state to a database is paramount. Player progress, inventory, world state changes, it all needs to be persisted reliably.
But database operations can be slow.
They absolutely can be, especially under heavy load. If not designed carefully, these database operations can quickly become a critical bottleneck, slowing down gameplay as the server waits to save or load data. Imagine lag every time you change zones or complete a quest because the server is struggling to write to the database.
So how do you optimize this?
Techniques include caching frequently accessed data in memory so you don't hit the database for every read, batching multiple database writes together instead of doing them one by one, and performing database operations asynchronously in background threads so the main game loop isn't blocked waiting for the database.
Finally, the platform choice. The source example used Java. Does it matter?
Well, the choice of language and platforms does have practical implications. The source mentioned Java was chosen for its ease of development, its automatic memory management, garbage collection, the extensive ecosystem of tools and libraries, and its strong cross-platform capabilities. These are valid reasons.
Well, the architectural principles aren't Java-specific.
Not at all. The fundamental concepts we've discussed, layering, modularity, handling concurrency, I/O strategies, persistence, are universally applicable. You could build the exact same architecture using C# with .NET or C++ AO or Python or Go. Each language and platform has its own strengths, weaknesses, and specific idioms for implementing these patterns, but the core architectural thinking remains the same. C#, for instance, is very widely used in game development, especially with engines like Unity and its own powerful .NET framework, providing similar capabilities for networking, concurrency, and more.
Okay, that's a great overview of server architecture. Let's transition now to object-oriented programming, OOP, and best practices in game development, maybe with a bit more focus on the C# context since it's so common.
Sounds good. OOP is, of course, a major paradigm, especially in languages like C# and Java. It's centered around this idea of objects, software entities that bundle together both data, fields or attributes, and behavior, methods or functions that operate on that data.
So programs become collections of interacting objects.
Essentially, yes. It's a way of modeling the real world, or in our case, the game world, through code by representing entities like players, enemies, items, or even systems as objects that have state and can perform actions.
What are the core features of OOP that are important here?
Several key ones. Encapsulation is fundamental, bundling the data and the methods that operate on it into a single unit, like a player class containing health data and a take damage method. It keeps related things together.
And related to that is information hiding.
Yes, protecting the internal details of an object from outside code, using access modifiers like public, private, protected, and C#. This is vital because it allows you to change how an object works internally. Maybe you change how health is stored or calculated without breaking the code that uses the object, as long as the public interface, like the take damage method signature, remains the same.
Like the car engine being hidden, but the pedals stay the same.
Exactly. It promotes code reuse, helps prevent bugs caused by unexpected external modification of internal state, and makes maintenance easier.
What about composition?
Composition is about building complex objects by combining simpler existing objects. This is the has-a relationship. A player object has an inventory object, which in turn has multiple item objects. You compose complex behaviors from smaller, focused parts.
Contrasted with inheritance.
Right. Inheritance is the is-a relationship. You create new classes, subclasses or derived classes, based on existing ones, superclasses or base classes. The subclass inherits properties and behaviors from the superclass. For example, a warrior class is a type of character class, inheriting common attributes like health and position, maybe adding specific warrior abilities. C# heavily supports this class-based inheritance, letting you build hierarchies of game entities.
And polymorphism. That sounds powerful.
It's extremely powerful. Polymorphism means many forms. It's the ability of code, often a function or method, to work with objects of different classes through a common interface or base class.
Like a draw method that can draw any shape.
Perfect example. You could have a draw shape method. You can pass it a circle object, a square object, or a triangle object, as long as they all inherit from shape or implement an iDrawable interface. The draw method doesn't need to know the specific type, it just calls the shape's own drawing method. This simplifies code immensely, promotes separation of concerns, the drawing logic is separate from the shape logic, and makes systems much more extensible.
What about open recursion? That sounds a bit more obscure.
It's a subtle but important concept in OOP. It refers to the way methods within an object can call other methods on the same object using special keywords like this in C# or self in Python. The key is that if a method is overridden in a subclass, calls using this from the base class will actually invoke the overridden version in the subclass. This is called late binding, and it allows base classes to define template behaviors that can be customized by subclasses in flexible ways.
Okay, so C# fully supports all these OOP features.
Absolutely. C# is fundamentally an object-oriented language, and these features are central to how C# applications, including games, especially those built with Unity, which heavily uses C# OOP, are structured.
But OOP isn't perfect, right? There are criticisms.
True, especially in the context of high-performance game development. Some argue OOP can sometimes lead to designs that are less cache-friendly because related data might be scattered across different objects in memory, hurting performance compared to more data-oriented approaches.
And complex hierarchies.
Yeah, deep inheritance hierarchies can become brittle and hard to understand or modify. Sometimes composition, has A, is preferred over inheritance for flexibility. Also, managing shared mutable state between objects can make concurrent programming more challenging compared to functional or data-oriented paradigms. But despite these critiques, OOP's benefits for organizing complex logic mean it's still a dominant and incredibly useful paradigm in game development.
Which leads us nicely into the solid principles. These are guidelines for doing OOP well, right? Particularly relevant for C#.
Exactly. SOLID is a mnemonic acronym for 5 core principles of object-oriented design, originally promoted by Robert C. Martin, Uncle Bob. They're hugely influential and considered foundational for writing understandable, flexible, and maintainable object-oriented code, definitely including C#. They help you avoid some of the common pitfalls of OOP.
Okay, let's break them down. S is for.
S, Single Responsibility Principle, SRP.
The idea that a class should only do one thing.
Sort of. More precisely, a class should have only one reason to change. This usually means it should have one primary responsibility or concern. The real aha moment with SRP, as the source material implies, isn't just, oh, clean code. It's realizing that by giving a class only one reason to change, you dramatically limit the ripple effect when changes do happen.
How so?
If your player class handles movement logic, combat calculations, and saving the game data to disk, a change required by the save system might force you to modify and retest the player class, potentially introducing bugs into unrelated movement or combat code.
So SRP separates those concerns.
Exactly. You'd have maybe a player movement class, a player combat class, and a player data persistence class. Now, a change to saving only affects player data persistence. It makes the code easier to understand, easier to modify, much easier to unit test effectively, and more flexible overall because changes are isolated.
Makes sense. Okay, O is for.
Open-close principle, OCP. This principle states that software entities, classes, modules, functions should be open for extension but closed for modification.
Open for extension, closed for modification. What does that mean in practice?
It means you should be able to add new functionality or behavior to a system without having to change the existing working source code of that system.
How do you achieve that?
Typically through abstractions like interfaces or abstract base classes. Think about a damage calculator system in a game. Instead of modifying the main damage calculator class every time you invent a new damage type, fire, ice, poison, holy, you design it so new damage types can be added as new classes that implement a common iDamage type interface. The damage calculator works with the interface, so it doesn't need changing when new types are plugged in.
So it's extensible without being modified.
Right. The benefits are huge. Enhanced extensibility, increased stability, you're not risking breaking existing code when adding features, and better adaptability to changing requirements down the line.
Got it. L. Lisley.
L. Liskov Substitution Principle, LSP, named after Barbara Liskov. This principle is fundamental to making inheritance and polymorphism work correctly.
What's the core idea?
It states that functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. In simply terms, a subclass should be genuinely substitutable for its base class without altering the correctness or behavior of the program.
So if I have code that works with a vehicle object, it should work exactly the same way if I give it a car object, assuming car inherits from vehicle.
Precisely. The car shouldn't violate any assumptions or contracts established by the vehicle base class. If the vehicle contract says accelerate increases speed, the car's accelerate method must do the same. It shouldn't say throw an unexpected exception or decrease speed.
Why is this so important?
It enables robust polymorphism. It ensures reliability because subclasses adhere to the contract of their superclass. And it guarantees predictability when you swap objects around, preventing subtle bugs or unexpected runtime errors that can be really hard to track down.
Okay, I was for.
I interface segregation principle, ISP. This one tackles the problem of fat interfaces.
Fat interfaces.
Yeah, large, general-purpose interfaces that declare many methods covering different responsibilities. ISP states that clients, classes using the interface, should not be forced to depend upon interface methods that they do not actually use.
So they break up big interfaces.
Exactly. Split large interfaces into smaller, more specific ones, each focused on a distinct set of functionalities. Imagine a huge iCharacter interface with methods for movement, combat, inventory management, dialogue, and AI behavior.
Okay.
Now, maybe a simple chest object only needs to interact with the inventory part. It shouldn't be forced to depend on or even know about the methods related to combat or dialogue. Instead, you'd have smaller interfaces like a movable, iAttacker, and inventory holder interactable. The chest would only implement or depend on iInventory holder.
What's the benefit?
It reduces dependencies, leading to much better decoupling between components. It allows classes to implement only the interfaces relevant to them, avoiding clutter. And it prevents changes in one part of a large interface, like combat methods, from forcing recompilation or changes in classes that only cared about another part, like inventory.
Makes sense. And finally, D.
D, dependency inversion principle, DIP. This is often misunderstood, but it's incredibly important for building flexible, decoupled systems.
What's the core idea? Depend on abstractions.
Exactly. Depend upon abstractions, not concretions. It has two main parts. One, high-level modules should not depend on low-level modules. Both should depend on abstractions, like interfaces or abstract classes. Two, abstractions should not depend on details. Details should depend on abstractions.
Okay, let's unpack that. High level shouldn't depend on low level.
Right. Think about your game manager, a high-level policy class.
Yeah.
It shouldn't directly create or depend on a specific SQLite database class, a low-level implementation detail.
Why not?
Because that tightly couples your game manager to SQLite. What if you want to switch to a different database later, like PostgreSQL or even a custom file format? You'd have to modify the game manager.
So how does DIP fix this?
Instead of game manager depending directly on SQLite database, both should depend on an abstraction, say an iData storage interface. The game manager uses methods defined in iData storage, like save game, load game. The SQLite database class implements the iData storage interface.
So the dependency direction is inverted. The low-level detail now depends on the abstraction defined by the high-level need.
Precisely. The game manager only knows about the iData storage interface. You can provide it with an instance of SWIDA database or PostgreSQL database or file system storage as long as they all implement iData storage. The game manager doesn't care about the concrete implementation.
And the benefits.
Massive benefits. Promotes loose coupling between modules. Increases flexibility enormously. You can swap implementations easily. Great for testing too, using mock implementations. Improves overall maintainability because changes in low-level details are less likely to break high-level policies. DIP is really key to building adaptable software.
So solid principles are ideals, but game development is often messy and deadline-driven. How do you balance architecture and practicality?
That's the million-dollar question, isn't it? There's definitely a common just-do-it mentality, especially in indie development or during prototyping phases. You hear advice like, don't get bogged down by analysis paralysis, just get something on screen.
Make it work first.
Right. For individual or very small projects, it's often more practical to follow that make it work, make it fast, make it pretty order. You can always refactor later, assuming the project survives and you actually allocate time for it.
That duct tape reality you mentioned earlier.
Exactly. Many successful games, especially from smaller teams or in their early stages, are often, let's be honest, held together with figurative duct tape and hope. Best practices like Solid become much more critical when multiple people need to understand, collaborate on, and maintain the code over a longer period. The cost of poor architecture multiplies with team size and project duration.
So it's about practical separation of concerns, not just theoretical purity.
Absolutely. Moving beyond just textbook OOP class hierarchies to how things are actually built effectively in games. For example, thinking of a game object not as one single monolithic class inheriting from game object base, but as a composition of specialized concerns.
Like the components idea.
Yes. You might have a component or object responsible for collision object, handling physics, shapes, and detection. Another component, rendered object, manages the visual representation, the 3D model, materials, shaders. Then the core game object logic orchestrates these, handling game rules like taking damage when the collision object reports a hit.
And this layering helps with complex features.
Crucial for them. Think about smooth interpolation in multiplayer games. The authoritative position might be managed by one component, while the rendered object smoothly interpolates towards it to hide network latency. Or having multiple representations, a detailed 3D player model for the main view, and a simple colored dot on a mini-map, both potentially driven by the same underlying game state, but handled by different rendering components.
Unity's component system is basically this, right?
Unity's game object component system is a very successful real-world example of this composition over inheritance approach, proving its effectiveness for building complex interactive systems.
This leads naturally into entity component systems, ECS. What's the deal with ECS? Is it just about performance?
That's a common misconception. ECS is a design pattern, first and foremost. It's not just a tool or a magic bullet solely for performance, although performance is often a major benefit. And it's not. New variations have been around for over 20 years in game development and simulations.
How does it differ from traditional OOP or component models?
ECS represents game logic in a very data-driven way, which is quite distinct from traditional object-centric, often event-based approaches. In pure ECS, entities are just simple IDs, unique identifiers. They have no data or behavior themselves. Components are pure data containers, like structs. They hold data for one specific aspect of an entity, e.g., position component, velocity component, health component. No behavior here either. Systems contain all the logic. They query for entities that have specific combinations of components, for example, find all entities with position and velocity, and then operate on the data within those components, e.g., update position based on velocity.
So data and logic are completely separated.
Completely. Entities are just IDs, components are just data, systems are just logic.
What are the benefits of thinking this way?
It leads to a codebase composed of many independent cooperating systems. This tends to make the systems themselves smaller, simpler, and easier to reason about and test. It enables truly iterative design. You can easily add new systems that operate on existing component data or add new component types without breaking existing systems that don't care about them. And it's fantastic for enabling complex, systemic gameplay where different systems interact in emergent ways based purely on the data.
And the performance gain, where does that come from?
The performance gains often come from data-oriented design (DoD) principles, which ECS aligns with very well. Because components are pure data and systems process entities with specific component sets, you can arrange the component data in memory very efficiently.
How so?
Instead of scattering data across lots of different objects all over the heap, like traditional OOP might, ECS frameworks often store components of the same type contiguously in arrays or tightly packed memory blocks. When a system runs, the movement system processes all entities with position and velocity. It can iterate through this contiguous data very quickly.
Because it fits well into the CPU cache.
Exactly. This maximizes CPU cache utilization, avoiding costly cache misses, which is where a huge amount of the performance gain comes from, especially when dealing with thousands or millions of entities.
But it's not easy to switch to ECS.
No, it's definitely not intuitive if you're used to traditional OOP. It requires a significant paradigm shift in how you think about structuring your code. This can make initial coding slower as developers get used to it. And as we discussed, many developers, especially under pressure, still prioritize getting things good enough quickly, using familiar OOP patterns over potentially more optimal but less familiar ECS approaches.
Is ECS relevant in C#?
Very much so. There are several high-performance C# ECS frameworks available. Unity's Data-Oriented Tech Stack, DOTS, includes a sophisticated ECS package as a core part of its future direction, demonstrating its relevance and power within the C# game development ecosystem, even with the learning curve involved.
So is it all ECS or all OOP? Or a mix?
Realistically, the best approach is often a hybrid one. Use ECS where it shines. For performance-critical systems, simulations involving large numbers of similar entities, like particle systems, crowds, bullets, or anywhere the data-oriented approach really simplifies the logic.
And use traditional OOP composition elsewhere.
Yeah, maybe use more traditional OOP with good composition patterns for more complex, unique, heavyweight entities where you have lots of specific logic tied to one thing, like the main player character, unique boss monsters, or complex UI systems. It's about choosing the right tool for the right job, leveraging the strengths of each paradigm within the same project.
Yeah, we should also remember Yale, Yi, and I.
Yes, you aren't gonna need it. It's a valuable principle from extreme programming, acting as a counterbalance against over-engineering. It's a caution against speculating too much about future flexibility needs and building complex abstractions or features that might be useful someday but aren't needed now.
Because it adds overhead.
It adds development time, debugging time, maintenance overhead, and complexity, often without providing any clear, immediate benefit. Build what you need now, keep designs clean and extensible. Following solid helps here. But avoid building specific features or layers of abstraction just because you think you might need them later. Address complexity when it actually arises.
What about prototyping? Is messy code okay then?
Prototyping is absolutely a legitimate and valuable practice. Writing slapdash code or throwaway code is perfectly fine, even encouraged for early design exploration, validating gameplay ideas quickly, or testing technical feasibility.
But there's a catch.
The critical caveat is understanding the purpose of that code. If it's truly throwaway, great. But if there's a chance that prototype code might evolve into or be kept as part of the final product, then it must be written well from the start, adhering to the project's architectural standards.
Or force a rewrite.
Even better, sometimes. One suggestion from the source was to write prototypes in a different language or environment than your main game engine. This effectively forces a complete rewrite before that functionality can be integrated into the main product, ensuring that only properly architected, production-quality code makes it into the final code base. It creates a clean separation between exploration and production.
That's a clever trick. Okay, let's move to our final major topic, the art of format design and tooling. Formats seem maybe less glamorous, but the source argued they're core to all software.
Absolutely fundamental. You might not think about it explicitly, but formats are everywhere. APIs are essentially formats for how you structure function calls and their arguments. File formats, .png, .json, .level, define how data is structured for storage. Network protocols define the format for data transmission over a network. Even programming languages themselves are formats for expressing instructions to a computer.
So getting the format right is critical.
It really is. Poor format design can severely limit what your system can do, make it hard to work with, or difficult to extend later.
The source distinguished between semantics and structure. What's that about?
Semantics is the meaning of the data. Structure is how it's represented. For example, the semantic concept might be a distance of 3 meters. The structure could be how you represent that in, say, JSON, value, 3 unit meters.
Oh.
JSON itself provides a simple general-purpose structure, objects, arrays, strings, numbers, but has no inherent semantic meaning. A simple structure like JSON is powerful because you can write reusable code, like a generic JSON parser, that works with any kind of data represented in that structure, whether it's game levels, user settings, or financial data.
But there are limits.
The limit is that the program using the data needs to understand the semantic meaning embedded within the structure. The JSON parser doesn't know that unit meters implies a distance. Your application code needs to interpret that. Designing simple structures that can effectively convey rich semantic meaning is a key part of good format design.
And implementability is crucial too. Keep formats simple.
Yes, hugely important. Formats and APIs should be as simple as possible to achieve their goal. If a format is overly complex, it's much harder for people to write code that correctly reads or writes it. This leads to more bugs, more support issues, and increases the workload for everyone involved.
The example was supporting polygons and NURBS.
Right. If your 3D model format supports both simple polygons and mathematically complex NURBS surfaces, then every tool or system that consumes that format, the modeling tool, the exporter, the game engine importer, the renderer, must implement code to handle both, even if they only care about polygons. This adds significant complexity and development overhead everywhere. Making clear choices about what your format will and won't support and managing those constraints is crucial for keeping things implementable.
You also need to consider managing interactions, how parts of the system connect.
Yeah, thinking about how many ways different parts of the system will interact, often mediated by formats or APIs. Will your video editor have just one main timeline format or allow multiple timelines that can interact? Are you designing your network protocol to support just player-to-server communication or also player-to-player?
Too few interactions is limiting. Too many is complex.
Exactly. Too few interaction points or too rigid formats can limit functionality and stifle creativity. But too many interaction possibilities or overly complex formats can create overwhelming complexity that's hard to understand, debug, and evolve. It's that Goldilocks problem, again, finding the just right level of interaction and format complexity for your specific needs.
And implementation freedom. Designing APIs so the internals can change.
Yes, this ties back to the open-closed principle and dependency inversion. Your APIs and formats should be designed so that the underlying implementation behind the API can change without forcing changes on the code that uses the API.
Think the text rendering example again?
Perfect example. The text rendering API should allow users to request text rendering with certain properties, font, size, color, text content, but shouldn't expose how it's actually drawn, bitmap versus vector curves. This allows the team implementing the text renderer to switch from bitmaps to TrueType rendering later without breaking all the UI code that uses the API.
Or the healthcare API not being tied to SQL.
Right. The API should deal in healthcare concepts. Patients, appointments, records, not database concepts, SQL queries, table names. This allows the back-end storage mechanism to change from SQL to NoSQL perhaps without affecting the applications using the healthcare API. It provides crucial insulation and flexibility.
What about the plugin system philosophy? Design your system to accept plugins.
Yeah, the source advocated for designing your system primarily as a world or environment that accepts plugins getting plugged in, rather than designing your core system to constantly have to plug into lots of different external systems or formats.
Why is that better?
It puts you in control. You define the stable interfaces and formats for your world, and others can write plugins that adhere to those interfaces to extend your system. This allows you to maintain the integrity and stability of your core system and environment, rather than being constantly dictated by the designs, changes, and potential instability of numerous external systems you're trying to integrate with. You invite others into your controlled world.
Okay, that makes sense. Finally, let's talk about the power of tooling. This sounds really important for big projects.
Absolutely paramount. Building extensive tooling, even tools that will never ship with the final product, is not just a nice-to-have for large software projects, including games. It's often essential for developer productivity, quality assurance, debugging, and simply understanding what the heck the complex system is actually doing. These tools are the unsung heroes.
What are some examples of essential tools?
The source gave several good ones. Black box recorders, tools that can subscribe to and log all significant events or state changes happening within the system. This allows you to perfectly replay a game session later to reproduce a rare bug.
Like a flight recorder for your game.
Exactly. Playback systems that can take that recorded data and simulate the events for automated testing or analysis. Python APIs or other scripting interfaces that allow scripters or testers to drive the system, automate complex test scenarios like simulating thousands of players hammering the economy, or perform repetitive tasks.
What else?
Real-time loggers and visualizers are crucial for giving developers immediate visibility into what the system is doing right now. Seeing AI decision-making processes, visualizing physics collision shapes, plotting network traffic, and even full simulators that can run the core game logic without the expensive rendering layer, perhaps at accelerated speeds, to perform stress testing, balance game mechanics, or train AI agents.
And a key benefit is enabling independent development.
Hugely important, yes. Especially for large teams or projects involving multiple studios or contractors. Let's take that jet fighter example again. You might have one team building the missile systems, another doing the radar, another doing the cockpit displays.
How do they test their parts before everything is ready?
Using these kinds of tools. The missile team can use a simulator, driven by recorded flight data or scripted scenarios, to test their missile's guidance logic and flight path without needing a fully functional radar system or a complete flight simulator environment yet. The cockpit display team can use playback systems or simulators to feed their displays realistic data before the underlying sensors are fully integrated.
So it catches integration issues much earlier.
Exactly. It allows teams to develop and test their components largely independently, verifying they meet their interface contracts long before the final complex integration phase. This saves immense amounts of time and resources by finding problems sooner, and this principle applies almost universally to complex software development, whether it's games, aircraft, financial systems, or web services. Good tooling is the scaffolding that allows multiple teams to build complex structures efficiently and reliably.
Okay, that wraps up the core content. So as we bring this deep dive to a close, let's quickly recap.
Sounds good. We've really covered the immense importance of thoughtful architecture in game development, explored the versatility of design patterns like composition and ECS, looked at practical lessons from pioneers like Ultima Online, and seen how modern big data solutions are tackling the scale of today's MMOs.
And we dove into those powerful, solid principles, seeing how fundamental they are for creating maintainable, flexible C# code or really good OOP code in any language.
It's clear, I think, that game development, like any really deep engineering challenge, rarely offers simple right or wrong answers.
No silver bullets.
No, none. Instead, it's this continuous dance of trade-offs. balancing performance versus flexibility, speed of development versus long-term maintainability, simplicity versus feature richness. True mastery comes from understanding these intertwined constraints and making wise, context-specific decisions for your particular project and team.
And remembering the ultimate goal isn't just to build a technically complex system.
Right. The goal is to build something that's engaging, immersive, and ultimately fun for the player.
So the final provocative thought to leave you with.
Perhaps it's this. Maybe the most effective way to achieve that goal of creating something fun is, as the source suggested, to actually have fun making it. That joy of creation, the intellectual stimulation of solving these hard problems, the passion and collaboration within the development team, maybe that energy somehow translates directly into the quality and soul of the final product, creating experiences that really connect with players.
A fantastic thought to end on. Thanks for joining us on this deep dive into the architecture that powers our favorite digital worlds. We hope you gain some valuable insights. Until next time.